Alright, moving on to 5.9. This should be another fairly short one, I think. But at the end of 5.8, we happened across this problem where we figured we were going to have to do some kind of u-substitution, except it's a little bit tricky. Like, what do you do with the limits of integration when you're doing a u-substitution? So I just wanted to talk about that. I mean, that's the subject of 5.9. So let's talk about it. There are really two ways to approach it. So the first way is to just evaluate the indefinite integral. Make sure to express the result in terms of the original variables. So you know, if you're using a u-substitution, but your original variable was x, make sure to express your result in terms of x, right? And then plug the result, or plug in the limits of integration into the function you got in terms of your original variable, right? So that's one way to do it. The other way to do it is you can use the fact that, well, remember that when you do a u-substitution, this is really kind of the format of the thing that you're doing a u-substitution of, and what you let u equal is g of x. That way its derivative is sitting right outside, right? So this whole thing becomes f of u du. Now look what happens to the limits of integration. If you let u equal g of x, then a is going to be g of a, and b is going to be g of b, okay? And so the benefit of doing it this way is that then you avoid having to back substitute. So once you've made your substitution, once you've made your u substitution, you don't have to worry about going back and substituting back in for x, right? You can just change the limits of integration accordingly. So what I want to do is, I have 5 examples. I want to walk you through these, and I might not do all of them both ways, but I'm at least going to do a couple of them both ways, so you can kind of get a sense for how this works, and maybe, you know, use the approach that you like best. So let's start with this one. We'll go 0 to 2, x times x squared plus 1 cubed dx. So what I notice is that the derivative of this stuff here is right there. So I'm going to let u be x squared plus 1, then du equals 2x dx. Well, so it's not exactly the derivative, but it's close, right? So, in fact, I can make it be the derivative by just fixing it that way, right? And then I've got 2x dx. I can replace that with du. This I can replace with u. So if I'm doing this using method 1, then I would say, all right, I'm just going to evaluate the indefinite integral and say x times x squared plus 1 cubed dx is equal to 1/2 times the integral of u cubed du, right? We replace this with u. This 2x dx is du, right? Okay. That's going to be 1/2 times u to the 4th over 4 plus c, although the plus c doesn't really matter since we're going to be plugging in limits of integration here in a second. So that's u to the 4th over 8, or in other words, since u was x squared plus 1, I can call it x squared plus 1 to the 4th power over 8, right? Now I can do my limits of integration. So I can say, all right, so then this thing should equal x squared plus 1 to the 4th power over 8 evaluated from 0 to 2, right? So I just found the indefinite integral first, and then I plug in the limits of integration when I'm done. If I plug in 2, I get 2 squared is 4 plus 1 is 5. 5 to the 4th power, holy schmoly, 5 to the 4th is 625. Well, that's not too bad. So I get 625 over 8. if I plug in 0, 0 squared is 0, plus 1 is 1, 1 to the 4th is 1, and 1 divided by 8, whoops, is 1/8. So I guess I get 624 over 8. 624 over 8 reduces to just 78. How beautiful is that? Wow. Okay. So there's method 1. Now method 2 would be to just continue on with the u substitution, right? We're going to say, let u be x squared plus 1. Well, if that's the case, then when x is 0, u is going to be 0 squared plus 1, right? So, so we'll say, if I call this thing g of x or whatever, the thing that I'm letting u be, then I would say g of 0 is 0 squared plus 1, which equals 1. And g of 2, the upper limit of integration, would be 2 squared plus 1, which equals 5, right? And so then this whole integral from 0 to 2 of x times x squared plus 1 cubed dx, it turns out that that's just equal to 1/2 times the integral from 1 to 5 of u cubed du. Right? And so that comes out to 1/2 times u to the 4th over 4. And I'll evaluate it from 1 to 5. So I'll call that u to the 4th over 8, evaluated from 1 to 5. And sure enough, right? If I plug in 5, now I'm back to where I was before. If I plug in 5, I get 5 to the 4th, which is 625. I know because I just did it. And if I plug in 1, I get 1. And that comes out to 624 over 8, which comes out to 78, right? Just like what we got before. So you can use either method. Either method you like is fine with me. Let's do another one. So let's do the integral from 0 to pi over 8 of sine to the 5th 2x times cosine of 2x dx. So in either case, I'm going to want to do a u substitution. And so I should think about what I want to substitute. The derivative of cosine is negative sine, so I can make this a negative sign and then just put a negative sign out here. However, I'm not sure how much good that's going to do me. That'll only take care of sine to the 1st power. I would still have sine to the 4th power left over, right? I mean, so it's not really going to do me any good. I'd rather go the other way around. Let u be sine 2x. And then du is going to be cosine 2x times 2, right? Chain rule. So I'm just going to call that 2 cosine 2x dx. So I suppose I do need a 2 here, which I can offset by putting a 1/2 there. But then I've got 2 cosine 2x dx, and all of that stuff, right, this together with this and this, can be replaced with du, and now this thing's just going to be replaced with u to the 5th power, right? Because u was sine 2x, so sine to the 5th 2x is just u to the 5th. Okay. So if I'm doing this using method 1, then I would say, all right, 0 to pi over, or actually I don't want to put the limits of integration on there at all. So I would just say, sine to the 5th 2x cosine 2x dx equals 1/2 u to the 5th du. Okay, and that's 1/2 times u to the 6th over 6. Or in other words, u to the 6th over 12. U was sine 2x, so this is sine to the 6th of 2x over 12. Okay, very good. So now I can say, alright, so then the integral from 0 to pi over 8 of sine to the 5th 2x cosine 2x dx should equal sine to the 6th 2x over 12 evaluated from 0 to pi over 8. Okay, so let's figure out what that is. 2 times pi over 8 would be pi over 4. Sine of pi over 4 is root 2 over 2, or 1 over root 2 if you prefer. 1 over root 2 to the 6th power would be 1/8, I believe. Right? So it's going to be 1/8 over 12 minus, now if I plug in 0, that's a little easier, right? 2 times 0 is 0, sine of 0 is 0, 0 to 6 is 0, 0 divided by 12 is 0. Okay. 8 times 12 is what? 96, is that right? Man. 96. Okay. So 1/96. So that's what we get using method 1. Method 2. For method 2, I'm just going to continue on with my u substitution and say, okay, so if u is sine of 2x, and if x is 0, then, when x is 0, u is going to be sine of 2 times 0, that's sine of 0, that's 0. So u is going to be 0. Maybe I'll write it this way. So at x equals 0, u equals 0, and at x equals pi over 8, u equals 2 times pi over 8 is pi over 4, and sine of pi over 4 is root 2 over 2, or I could call it 1 over root 2 if I like. So I am going to call it 1 over root 2. Right? Okay. So then, integral from 0 to pi over 8 of sine to the 5th 2x cosine 2x dx is just 1/2 times the integral of u to the 5th du, which is 1/2 times u to the 6th over 6. That's u to the 6th. Sorry, I forgot the limits of integration. It's this, from u equals 0 to u equals 1 over root 2. So it's this evaluated from u equals 0 to u equals 1 over root 2. So it's u to the 6th over 12 evaluated from 0 to 1 over root 2. Right? So then you can plug in 1 over root 2. 1 over root 2 to the 6th power is 1. Root 2 to the 6th power is 2 cubed is 8, so it's 1/8 over 12. I know I already went through that, I just wanted to double check my math. And then if you plug in 0, of course you get 0. So again, you get 1 over 96. Okay, alright. So I have 3 more examples to give you, but I'll tell you what, I'm not going to do method 1 anymore. I think I'm just going to stick to method 2, only because I think method 2 is maybe a little bit more confusing at first. However, it is really nice. It's a really nice method. It's nice and elegant, I think, and it'll come in handy later on in later calculus courses that you take. So let's practice with method 2 from now on. I'll just do the method 2 way. So let's integrate from 2 to 5, 2x minus 5 times x minus 3 to the 9th dx. Now this one's interesting just because of the u substitution portion of it, because derivative of x minus, I don't have to use a u substitution for this. I could raise x minus 3 to the 9th power and then multiply that result by 2x minus 5. It's just that it's going to take you a long, long time to do it. So I'd rather avoid that if I can. Which means that the thing that I want u to be is probably x minus 3. That way I just have u to the 9th. Okay? So if I let u be x minus 3, now the trouble with that is that then du is just going to be dx, and what do I do with this other stuff? But we saw an example like this a few sections back, and what you do is you just solve for x in terms of u so that you know what to replace this with. So let's go through it. I'm going to say let u be x minus 3, then du equals dx, but also x equals u plus 3, right? If you add 3 to both sides, x equals u plus 3. So 2x minus 5 would equal 2 times u plus 3 minus 5. Okay, that's going to be 2u plus 6 minus 5. 6 minus 5 is 1, so it's going to be 2u plus 1. Okay, so I can replace 2x minus 5 with 2u plus 1, and I can replace x minus 3 with u, and I can replace dx with du. So that'll get rid of all of my x's. Now my limits of integration. If u equals x minus 3, then at x equals 2, so at x equals 2, u equals 2 minus 3 is negative 1, and at x equals 5, u equals 5 minus 3 is 2. So making all of those substitutions now, right? I'm going to say I am now integrating not from 2 to 5, but from negative 1 to 2. I can replace the 2x minus 5 with 2u plus 1. I can replace x minus 3 with u. And the dx I can replace with a du. Now that may not seem much nicer to you at first glance, but notice that you can distribute u to the 9th really easily now, right? So this is just the integral from negative 1 to 2 of 2u to the 10th plus u to the 9th du, and that's really simple now. So this is going to be 2u to the 11th over 11 plus u to the 10th over 10 evaluated from negative 1 to 2. Okay, so if I plug in 2, holy schmoly, 2 to the 11th times 2 is really 2 to the 12th, right? What is 2 to the 12th power? 2 to the 12th power is 4096 divided by 11. Plus 2 to the 10th, 2 to the 10th is 1024 divided by 10. This is 512 over 5. Okay, that's what happens when I plug in 2. If I plug in negative 1, negative 1 to the 11th power is negative 1. Negative 1 times 2 is negative 2, so I get negative 2 elevenths. Negative 1 to the 10th power is a positive 1. So I'm going to get plus 1 tenth. So I suppose maybe if I had left that as a denominator 10 instead of simplifying, I could have called this 1024. I could have called this 1024 over 10. That would make the arithmetic a little easier here. So I've got 4096 over 11 plus 2 over 11. That's 4098 over 11. And then I'm going to have a 1024 over 10 minus a 1/10. So that's plus 1023 tenths. Oh goodness, I don't even want to know. What is this once we get common denominators and such? Let's see. 4098 over 11 plus 1023 over 10 equals 52,233 over 110. That's approximately 474.8. Okay, but there you go, right? So there's the answer to part C. Okay, let's do another one. Two more. Integrate from 0 to 3/4. Let's do dx over 1 minus x. Maybe we don't even need a u-substitution for this one. This would just be 1 minus x to the negative 1 power. But you do kind of have a little, well, okay. So here's what I'm going to say. So this is 0 to 3/4 of 1 minus x to the negative 1 dx. So I'm going to let u be 1 minus x. So then du is going to be negative dx. So I need to get a negative dx in there. So I'm going to put a negative there and a negative there. So then negative dx is going to become du. This thing is going to become u to the negative 1. So I'm going to get negative integral. Oh, and I should figure out what my new limits of integration are, right? So if u is 1 minus x, then when x is 0, u is 1. And when x is 3/4, u is 1 minus 3/4. 1 minus 3/4 is 1/4. Okay, negative dx is going to become du. This is going to become u to the negative 1 du. Okay. Oh, but I've got to, I was thinking about differentiation. I've got to integrate that. Oh, well then that is easier to just think of in terms of a natural log, right? Instead of thinking about it this way. But all right, that's fine. U is still 1 minus x though, right? And du is still negative dx. So I've still got this scenario. So let me redo this, right? So I'm going to have negative integral of du over over u. That's what I've got. Going from 1 to 1/4. Okay, so that's negative ln of absolute value of u. Okay, evaluated from 1 to 1/4. Very good. If I plug in 1/4, oh, that's so nasty. I get negative ln of 1/4. If I plug in 1, though, that's a little easier. Ln of 1 is just 0, so this is minus 0. So I just get negative ln of 1/4. And in fact, this negative 1 I can make an exponent, and 1/4 to the negative 1 would just be 4, right? So actually I could just call this ln of 4. And give that as my final answer. Okay, one more. Let's integrate from 0 to ln of 3 e to the x times 1 plus e to the x to the 1/2 power. Alright, so the thing I want to get rid of is the 1 plus e to the x. So if I make that u, then notice that the derivative of this thing is sitting right there, right? Derivative of 1 plus e to the x is just e to the x. So that'll be very nice. So let's let u be 1 plus e to the x. Then du is going to be e to the x dx. So e to the x dx is going to be replaced with du. This is 1 plus e to the x is going to be replaced with u. What do these things become? So I'm going to have this. When x is 0, u is, well, e to the 0 is 1, 1 plus 1 is 2. So u is going to be 2. when e is ln of 3, e to the ln of 3 is just 3, and 3 plus 1 is 4. Right, so my limits of integration become 2 and 4. And I'm going to have u to the 1/2 du, right? This thing and this thing together made up the du. This thing was replaced with u, so u to the 1/2 du. Okay. Good. So that's, it's going to be u to the 3/2 divided by 3/2, or in other words, 2/3 u to the 3/2, evaluated from 2 to 4. Now if I plug in 4, square root of 4 is 2, 2 cubed is 8. If I plug in 2, square root of 2 is, well, square root of 2. Square root of 2 cubed is square root of 8, I guess I could call it, right? Or if you want, you could call this 4 times 2. Square root of 4 is 2, so you call it 2 root 2. But you get 2/3 times 8 minus 2 root 2. If you wanted, you can distribute the 2/3, I guess, and call it 16/3 minus 4 root 2 over 3. I don't know. Whichever one is your favorite way to express it is fine with me. But that's that, right? So that's it for part E. And that's all I have to say about 5.9.